Okay, I've been a little bit slow on posting videos, but I did get the video from last class up this morning. I continue to have issues with the bandwidth here on campus and trying to upload, and it takes forever, so it's better for me to just do it at home, but then when I get home, I forget to do it, so anyways, they're up. We have a lot to do today. If we're lucky, we get through 8.1. All right, so last time what we were doing was we were talking about, oh, and I sent out reviews because we have an exam a week from today. And that was so that we could have a test grade before drop date, I believe. It's on Wednesday, yes. All right. So last time we were talking about sequences and we talked about notation, finite sequences versus infinite sequences. And we started talking about common sequences, and we had looked at the evens and the odds, right? The evens and the odds. So now I'm going to put up some more sequences. We may not be able to have the fun that I plan on having, where we go around the room and we ask and we spend a lot of time. We really don't want to get too bogged down here. So how about this? Right, can we come up with a formula for this? So when you had the evens, remember the evens, even 2, 4, 6, 8, 10, right? They were increasing by 2 each time, right? Add 2, add 2, add 2. And then with the odds, it was also add 2, but we started at a different place. So we did something like 2n plus 1, 2n minus 1, something like that, right? So here, do you see anything? They all go up by 3, right? In other words, these are all multiples of 3. So I'm going to start my formula by saying, okay, a sub n is going to be 3 times n, because they're all multiples of 3. And then I just got to make sure that when I start with 1 that I get 3. So when I start with 1, right, n equals 1, I get 3, n equals 2, I get 6. So that works, right? Then I can try and do a different one where I shift this sequence over. Like let me start at 12 instead. 12, 15, 18, 21. And now if I want to do that, again, I notice they each grow by 3, right? Add 3, add 3, add 3. They're all multiples of 3. The problem is this formula won't work. I know that they're multiples of 3, but I need to start at 12. So what do I add to this or subtract? Add 9. Add 9. And that way when you plug in 1, you get 12. And then you know from there on out they'll keep going up by 3. Understand? And we can do this for any multiple, anytime we have multiples. So let's see. How about this one? How about 0, 5, 10, 15? Those all go up by 5 each time, right? So these are all multiples of 5. And that won't work because if I do that, let me make sure I thought my TV was going to be here, so I think this is as far as I can go. That won't work, will it? Okay, so what do I need to do? I need to subtract 5. Subtract 5. That way when I plug in 1, I get 5. Take away 5, I get 0, so I get my first one. All right, and then they'll just keep going up. One more. Negative 14, negative 7, 0, 7, 14. Those go up by how much each time? 7. So we've got a sub n equals 7n, but I need to start at negative 14. Minus 21. That way, when you plug in 1, you get 7. Take away 21 is negative 14. Then they keep going up. Okay, good. Understand? If we have something that goes up by the same amount, we should be able to come up with a formula for it. All right, the next thing I want to talk about is this. I'll make that bigger in a second. How about something like this? Can you come up with a formula that would generate that sequence? -1 to the power of n. This is an important sequence. Okay, very important sequence. It's actually the next thing on our notes. This is what's going to be referred to as an alternating sequence. It's alternating in sign, right? It goes negative, then positive, then, well, -1, then +1, then -1, then +1. So the way to make that happen is to take the number -1 and raise it to the nth power. And we can just check it. If we do a sub 1, when we plug 1 in here, we get -1 to the first power, which is 1. -1. But then when you do a sub 2, that's -1 squared, and when you square -1, you get +1. And we do -1 cubed, you'll get -1, right? And so on and so forth. It makes it flip back and forth, right? Flap back and forth. So this is a formula that would work for this sequence. It would create an alternating sequence starting negative, right? Starting negative. Is that the only formula? Could we come up with something else? Well, there are other adaptations of this that you can use. Like, check this out. If I do -1 to the n plus 2, that would also work. Why?
Start with an odd.
Yeah, I'm still going to start with an odd, right? I'm still going to start with an odd number here. If I plug in 1, I would get a 3. -1 cubed would give me -1, right? I could do, then plug in 2. -1 to the 2 plus 2 is 4, so -2 to the 4th is +1. So it would again start switching. In fact, we could do a sub n equals -1 to the n, and then what we could do here is we could add or subtract any even number. So if you did like n plus 6 or n minus 8, all of those would create this sequence. You all okay with that? Comfortable with the idea? Yes? Okay. Now, let's look at another one. How about if I wanted that sequence, but I wanted to start positive, not negative? Okay, so now I'm starting with +1, not -1. So we can still use the -1. We can still use the -1 to a power, but it's going to be a little different. What should it be? Odd number? How do you mean?
Like n plus or minus.
So -1 to the n, and then let's just start with the basic one. How about +1? How about that? What happens when I plug 1 into this? I get 2, right? -1 squared, +1. What happens when I plug 2 into this? I get 3. -1 to the 3, -1. So this right here will generate this sequence. And if we generalize it, we could do -1 to the n. We could have said +5 would have worked, right? Because if we plug 1 in here, we're going to get what? Even. If we plug 2, we're going to get odd. 3 even. 4 odd, right? So on and so forth. So generally speaking, we could do -1 to the n plus or minus any odd number. Bless you. Bless you. Okay, and this is in your notes. Let me make that bigger for you. Try one more. Okay, so this is an alternating sequence. And if you want to start negative, then the generic formula we use is -1 to the n. But you could actually do -1 to the n plus or minus any even number. That's what I just put on the board. And then the one below that is starting with positive. We're going to use that for the rest of the chapter. So are y'all okay with that?
Yes.
Anytime we want to alternate something. Okay, so let's try this. Let's go 10, -15, 20, -25, 30, -35. You get the idea, I think. Okay, So the way you approach this, the way I approach this, is that I don't pay attention to the numbers as much as I first pay attention to whether or not I have something alternating. So do y'all see I have alternating? Positive, negative, positive, negative, positive, negative. So I can make that happen, right? I can make that happen. To make that happen, what I'm going to do is take -1 and then raise it to a power. I need to start positive, right? So I'm going to use this. So I just do n+1 here. That takes care of the alternating. Now I can focus my attention on just the numbers. 10, 15, 20, 25, 30, 35. They keep going up by 5, right? So I just do times 5n. Now hold on, will that work? If I plug in 1, I'm going to get 5, right? I need 10, so I need to do what? What do I need to do? Add how much? Add 5. I need to add 5 to that 5n. Now when I add 5, very important, I put this in parentheses. See, what we're doing is we're combining the two ideas together now, right? This will make it jump by 5 each time, starting at 10, and this will make it alternate. Questions? There's many different ways we could write this. You could try and distribute this through, but this is really the way we're going to wind up leaving it at the end. You could even do this. You could pull a 5 out. You could go -1 to the n+1. Then back here you could do n+1. See, that's just factoring a 5 out of both of those and bringing it out in front. What you cannot do is put those together because they don't have the same power, right? So you cannot. Order of operations, right? Order of operations says you must do exponents before multiplication. So don't turn this into -5 to the n+1. That's not right. We all right? Okay, let's look at some other common sequences, ones that we need to be, I guess, familiar with. So I already talked about, I'm going to make this bigger again. I already talked about this one. K times n. That's like 5n, 3n, 2n, right? We've already talked about those. Now, powers we have not seen. By the way, this was a typo in my notes. I was looking at my notes today. For some reason, there's a typo on this in my notes. This is correct. What I had was all, I don't know what the hell I had there. It was wrong. And I've had it there for years, so I don't know why it took me so long to recognize it, but. Okay, so look at this generic formula, k to the n. Right, this is a generic formula. So what this is a sequence where you have, now k here is a constant. N is the thing that's changing, right? N's going to start with 1, then 2, then 3, then 4. So we'll have k to the first power, then we'll have k squared, then we'll have k cubed, then we'll have k to the fourth, and this will go on and on forever, right? So an example of that, if k is 5, right, then if I have the sequence 5 to the n, right, k is 5 here, then this will give us 5, 5 squared, 5 cubed, and so on and so forth, which I have written down there. 525, 125, 525. Wait a minute. Is that right? No, that's not right, is it? That should be what, that last number? 625, man. I'm on, but that's old. That's old. Okay, 625. Okay, powers, right? Let me give you another example of this one, okay? This time I'm going to give you the sequence and see if you can give me the formula, all right? So how about this one? 1/3, 1/9, 1/27, 1/81. Do you recognize those as all powers of something? What's the formula? Well, this is 1/3 to the first power, right? This is 1/3 squared. This one is 1/3 cubed. This one is 1/3 to the 4th, and so on and so forth, right? You have to recognize that those are all of those powers. And therefore, my formula is 1/3 to the n. And that works, right? If I plug in 1, I get my first piece. Yes? Uh-huh.
Also just say 3 to the negative n?
You could say 3 to the negative n, exactly. You could rewrite the inside as, you could rewrite this fraction as 3 to the negative 1, couldn't you? That's the same as this. And then when you have something to a power, you multiply the powers, right? So this would be 3 to the negative n. Exactly. That would be completely fine to write it that way. Okay, good? All right, I'm going to try a little, I'm push a little harder. Let's see how this goes. How about, how about this? -3, 1, -1/3, 1/9, -1/27, ... This one's a little harder. All right, first thing I'm going to notice it's alternating. It is alternating, right? Negative, negative, positive, negative, positive, negative, positive, right? Let's take care of that first. How do we create a sequence that alternates starting with negative? -1 to the n. Or n plus or minus any even number, but that's the cleanest one, right? -1 to the n. Okay, then ignore the negatives here, right? And just look at the numbers themselves. These are these are powers of 1/3, right? Didn't we? Right? So like, I'm ignoring the negatives right now. This is 1/3 to the first power. This is 1/3 to the second. This is 1/3 cubed, right? And then, of course, it looks like it would be to the 4th to the 5th. Now, what is this? That's 1/3 to the 0, isn't it? This is 1/3 to the 0, because any non-zero number raised to the 0 is 1. And what's 3? 1/3 to the -1. You see that? If you take a fraction, raise it to the -1, it flips over and you get 3. So, no? Yeah? Okay. So do you see that all of these are, in fact, just powers of 1/3? But we need to start where with our power? -1. So let's see. I'm going to have I'm going to have 1/3 raised to the n, but I don't want to start, when I plug in 1, I actually want to get -1, don't I? So what do I need to do this? Subtract 2 from it. And now, if I plug in 1, I get -1. If I plug in 2, I get 0. If I plug in 3, I get 1. Do y'all see that that'll create these powers here? Okay. Okay, so that's powers of k. The next thing is kth powers of n. It's a little different. So instead of having that, we have this. It's n down here, and k, our constant, is up top. Now, I'll be honest, this one doesn't come up as much in this chapter, but let's at least look at it. So this would be, you're taking some number, right? What's the first number I'm going to plug in? 1, and I'm raising it to the k. Then I'm going to plug in 2 to the k. Then I'm going to plug in 3 to the k. Then 4 to the k, and so on and so forth. There's a big difference between these two, right? So as an example, let's say, I did there, k was 3, right? Let's say k was 2. If k was 2, we would have a sub n equals n squared. That's basically what it would be. And so that sequence would be 1 squared, 2 squared, 3 squared, 4 squared, and so on and so forth. Now, there's actually so many sequences out there. I mean, there's an infinite number of sequences that you could think of. I'm only looking at the common ones that we need for this chapter. There's a website, I think it's called the Encyclopedia of Sequences, where you can just like type in a sequence and it will try and figure out like where it is, and there's famous ones, and yes?
On the last one, why did you do n-2?
Because the first number here, right, this number needs to come when we plug in 1 for n, right? When I plug in 1 for n, I need this to happen. So this first piece, when I plug in 1 here, get -1 to the 1, that gives me a negative number, right? But then I need it to be 1/3 to the -1 power, and see if I just left that as n, then that would be -1 to the first power, right? So to make it the -1 power, I subtract 2. One thing I didn't point out is that these numbers, just look at the exponents, -1, 0. These numbers, we're jumping by how much each time? How much are we jumping by each time? 1, which is why I put 1n, right? I jump by 1. If I jump by 3, then it would be 3n. If I jump by 5, it would be 5n. And then this is going to control where we start. Does that help a little bit? Yeah? Yeah, these ideas start to come together really quick. Like we have to kind of... Is there another question?
Why did you put the -1 to the n and just that instead of just making it a -1/3?
You could have done something like that. Put the -1 together in here, or just looked at it as these are -1/3 being raised to powers. There are a lot of different ways that you could have done this. I'm trying to show you the way that I think, at least for me, makes most sense. I start always by saying, let me take care of alternating first. Get that taken care of. Now let me focus on numbers. Now, could we manipulate this? I mean, there's a lot of different things we could have done. Like this is the same as, isn't that this? Isn't this this? So that's that, right? When you have this, I could split it up. Remember, if you have the same base multiplied 2 exponents, you add these together, don't you? So this becomes this, right? I'm just kind of going backwards. Now, both of these are raised to the same power, aren't they? So I can put those together. I could write this as -1/3 to the n. And then this, what is this really? You flip it and then square it. 9. That's another formula you could have had. Now, most people are not going to look at this and be like, oh yeah, that's 9 times -1/3 to the n. The way they're going to get it is by breaking it apart into pieces. You see what I'm saying? Like it's not as obvious to get to this straight away. We could simplify this to this, and we should be comfortable doing this, and we will have to do things like this later. But for right now, we want to at least just get the formula, right, for it. Okay? All right. So I already talked about alternating sequences, right? I already talked about alternating sequences, but I want to stress again that anytime you have a sequence and you want it, and it starts with a negative and then switches negative, positive, then all you need to do is put a -1 to the n out front, and then go figure out what the b sub n is, the thing that creates the numbers. So for the problem we just did right here, right? This was the part that we found that was the part that creates the negative, and then this is some b sub n, it's some sequence formula, right? Some other formula. And then if we want to do it the other way and start with positive, then we just change that to n plus 1. Okay. Factorial. Show of hands, how many of you have heard of factorial before? Yes? So okay, that's quite a few of you. So when we have factorial comes up, I think the first time most people see it is in statistics classes, but the idea of factorial is this. If I write 5 with an exclamation point, right, like that, mathematically that doesn't mean you yell 5, right? That means 5 times 4 times 3 times 2, and you don't have to put times 1, but I always like to go all the way down to 1. Right? 5 times 4 times 3 times 2 times 1. That's what factorial is. It's a condensed notation for that operation. So let's figure out what this is. Let's see. I can do these two together, that's 20, right? These two together, that's 6. 20 times 6, this is 120. 5 factorial is 120. Okay? I could keep going, but let me go, I go bigger, I'm gonna go smaller. How about 4 factorial? What's 4 factorial? 4 times 3 times 2 times 1. So 12 times 2, 24? Okay. How about 3 factorial? 3 times 2 times 1, 6. 2 factorial? 2 times 1, 2. 1 factorial? 1, right? 0 factorial? 0 seems reasonable, right? It's 1. I'm going to put a box around that because this is where factorial stops making sense for most people. And so right now, I want you to just take that on faith, all right, just for the next 2 minutes while I talk, all right? 0 factorial is defined to be 1. Now, it doesn't follow the pattern, does it, right? It doesn't follow the pattern. Do you agree? Okay. So before I get into that, let's just try and see if we can figure out a general formula for what n factorial is. N factorial, right? 5 factorial, you start with 5, right? So here I would start with n, right? And then I multiply that times what? 1 less than that was, right? So I'm going to multiply that by n minus 1. And then I multiply that by what? Now we take away 2 from that n, right? N minus 2. And how many of these am I going to do? Well, it depends on it depends on n, doesn't it? So I'm going to put here, I'll do one, no, I won't do one more. Dot, 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 meaning I'm going to repeat that pattern of subtracting until I get to where? When do I stop? When I get to 1, right? 1. Right? All of these break down until I get to 1, till 1, till 1, till 1, except for that last one. That last one's like, ugh. Okay? So this is the definition of n factorial. Okay? Now, it's n factorial is defined, at least for you, most of you who've seen it, n factorial is only defined for non-negative integers. In other words, in order to talk about factorial, you can only do 0 factorial, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, right? You can only have non-negative integers, and then you can do a factorial. Like, what is this? What is 1/2 factorial? Well, it doesn't, I mean, that doesn't make sense, does it? If we, like in the way that you learned it, right? Does this make sense? Let's try it. What would happen if we just tried this formula? 1/2 and then multiply that by, yeah, 1/2 minus 1, which is negative 1/2, right? Wait a minute, we're supposed to stop when we get to 1. We're at negative 1/2. Okay, so factorials, at least in your mind, right? Factorials have never made sense for fractions, right? Okay, so now the class has to decide. We're either going to go off on a tangent right now, it's going to take us 10 minutes, or we just live with this and move on. Live with this and live with this. The fact that we can't do fractions as factorials, and live with 0 factorial is 1, we're not going to question it. So how many of you, the two options are, let's live with this, and who cares, fractions, we don't care. Or, you know what, I'd like to know why 0 factorial is 1, and what's this deal with fractions. So how many of you okay just moving on? Okay, how many of you want to see? Well, that's close, man, that is close. I have it, it's right there. Yeah.
Do you have it do you have this explanation in a previous?
Yes.
I don't know if it's in another video. I've been doing it more recently than I have in the past. I'm going to do it. I'm going to just briefly do it, okay? I'm going to briefly do it. I mean, it was a democratic decision, but it was, you know, I had to break the tie, so.
The video for future class.
Look, the whole idea comes from this. Factorial, the way that you learn it, is like the simple idea. This is a simple idea, 5 times 4 times 3 times 2 times 1. But actually, factorial comes from somewhere else. It comes from a function called the gamma function. So the gamma function, this is the gamma function. And it is really strange when you see it. All right? It's this right here. That's capital Greek letter gamma. Gamma of x equals the integral from 0 to infinity of t to the x minus 1 times e to the negative t dt. Okay, shit. That's an improper integral, right? That's an improper integral. That's like the area underneath some curve from 0 to infinity, right? Somehow, the gamma function, you give it a value of x. That value of x goes right here. Right here. Bernoulli is the person who came up with this, right? So this is the x, right? That's the x. You input a number right here, and then you evaluate this improper integral. Okay? And what turns out to be the case is that gamma of x equals x minus 1 factorial. That is the relationship between gamma and factorial. So let me try and illustrate this with a specific example. If we wanted to know what 2 factorial was, right? We all know what 2 factorial is, right? From the way we were taught. 2 factorial, this would need to be a 2, which means x would need to be what over here? 3, right? Gamma of 3. So gamma of 3 would be 3 minus 1 would be 2 factorial. Now, how do you find gamma of 3? You replace that with 3. So we do integral 0 to infinity t 3 minus 1 e to the negative t dt. This is integral 0 to infinity t squared e to the negative t dt. And then you have to figure out what this is. This would be partial fraction. This would be integration by parts twice to do this integral. We could do it. I'm not going to spend the time doing that, all right? But I will go to Wolfram alpha. I thought I put that here. Okay, so I will go to Wolfram alpha. I already have it ready to go. So Wolfram alpha, here's the integral 0 to infinity t